students, and in this video we are going to talk about some inequalities. Okay, so the first inequality which we are going to do here is called a Cauchy-Schwatz inequality. Cauchy-Schwatz inequality. So probably some of you have heard about this because it is a very famous inequality, but in case you did not, and since we are going to use it a lot of time in the course, so we are going to talk about this inequality. Okay, so what is this? So essentially, let's say you have an inner product space, right? So V, let's say V and this inner product with this function is an inner product space. Okay, inner product space, let's say inner product space. Clear? Now in this inner product space, let's say that you have two vectors v and w. Okay, so for all u and v in v, so you start with any two vectors u and v in v, this inequality should hold. So the inner product of u and v, okay, the square of it should always be dominated by the inner product of u and u times the inner product of v and v, right? So this is what Cauchy-Schwatz inequality says, and it's very simple. And of course the thing is how to prove this thing. Okay, so this is a Cauchy-Schwatz inequality, and the point is this: how do you prove such a inequality, right? So before I do that, one simple remark I want to put down here. Remark: see, every inner product gives rise to a Euclidean L2 norm, right? So we know that every inner product gives rise to an Euclidean should be big, Euclidean, that is L2 norm. Okay, L2 norm, right? So and the thing is where one defines the norm as this, where one defines the norm of u as the square root of inner product of u with itself. Okay, so and you always know that u with itself is always non-negative real number, so all of this makes sense. Okay, so in terms of norm, so in terms of norm, so basically if you are working in a norm linear space, that is, okay, the Cauchy-Schwatz inequality takes this form. So the inner product of u and v is always dominated by the norm of u times the norm of v. Clear? So this is the Cauchy-Schwatz inequality, right? Now let's look at what is the proof of such an inequality. Okay, so the first thing, proof. Okay, see, first of all, u and v are any two vectors, right? So this is basically a vector space. So u and v are any two vectors, right? So let's say let u and v so basically I start with any u v in v. Okay, it doesn't really matter what, but any two arbitrary u and v. So let u and v be such that u equals to lambda times v. What does that mean? It means that u and v are linearly dependent. So let's say they are linearly dependent. So please understand what we are trying to do here. For any two vectors u and v, we want to prove that the norm, the inner product of u v, the square of that, is always dominated by the inner product of u with itself and the inner product of v with itself, right? So and for any two vectors u and v, they either will be linearly dependent on each other, or they are linearly independent. So the first case is this, that let's say they are linearly dependent. So u equals to lambda times v. So in this case you see that norm of u times v, this is nothing but u times lambda v times v, right? And that is nothing but lambda times v with inner product of itself, right? So in this case you can see that what happens is, if I am taking the mod and square of that, so the mod and square of that, it becomes lambda square and the square, right? So this is nothing but equality. T. So basically you can actually write it like this, and okay, so let's do the other part. And norm of the inner product of UU dot the inner product of VV, let's just calculate that. So it is the inner product of lambda V times lambda V dot the inner product of V and V, right? So that will actually give you lambda V is lambda square, the inner product of V and V, the inner product of V and V times the inner product of V and V. So you do realize that this is nothing but lambda square, the inner product of V and V square. Okay, so those two are same. So essentially the equality holds in this case. Equality holds in this case. Okay, so you see this less than equals to holds in this case. Okay, so what happens that if they are not linearly dependent, so basically they can be linearly independent also, right? So this is case 2, right? If they are linearly independent, then look at this factor, U should never be equals to lambda times V for any lambda in R, right? There should not be any lambda in R such that U equals to lambda times V. Of course, you see, if one of them is 0, then nothing doesn't matter. I mean, the equality holds. So basically we are assuming U and V are non-zero, right? So then U is not equals to lambda times V. So in this case, look at this inner product, U minus lambda V, U minus lambda V, the inner product of this particular vector. This inner product is of course always going to be strictly positive, because if equality holds, so basically the inner product is equals to 0 holds, then U has to be equals to lambda V, right? So for any, so I can say that the inner product of V minus lambda V and an inner product with itself is always positive for any. So I can say this holds for any lambda in R, right? This holds for any lambda in R. Of course, I am assuming U and V is not 0, so that's there. Okay, lambda in R, right? So you see, now what is happening is this. If this is true, then let's break it up. You see, if you break it up, it is U inner product with U, right? Minus 2 times lambda U inner product with V plus V inner product with V. This is what we are going to get, which is strictly positive, right? Sorry, there is a lambda square here. Okay, lambda square. Now if we write down, you see what is happening is this. So this is nothing but, you think of this as A, this as B, and this as C. Okay, so you have this relation lambda square C minus 2 lambda B plus A is strictly positive. So this is a quadratic, right? This is a quadratic. Okay, and if this is positive, it means that it is never achieving 0 for any lambda. What does that mean? It means the discriminant is always going to be negative, which means that B square, right? B square minus AC is going to be negative. Okay, what does that mean? That will imply that what is B? Okay, what is B here? So let me just put it this way, that if we write it like this, this particular thing happens. Okay, let me write it this way. Okay, so if we denote this as now what happens is, what is B? B is nothing but UV, the square of that, okay, minus A is UU, U inner product with U, times C is V inner product with itself. Okay, so this is always has to be negative. What does that imply? It implies that the inner product of UV, the modulus of that, is always dominated, square is always dominated by the inner product of U with itself times the inner product of V with itself. Okay, sorry, equality does not hold here. Okay, so the inequality holds here, and hence, so you do realize that when they are dependent, then the equality holds, and when they are independent, then of course the strict inequality holds, and hence we have this Cauchy-Schwatz inequality. So is that clear that the Cauchy-Schwatz inequality holds in a inner product space? This sort of thing happens, and of course if it is a norm linear space, then you can of course write it in terms of norm. So that is there, right? Okay, so let me put a small remark here. This is like not a very important remark, but I should make this in any case. See, if u and v is in R2, okay, let's say R2 or Rn, doesn't matter, R2, let's write it as Rn. Okay, if u and v is in Rn, then you can talk about the inner product of u and v, which is nothing but the dot product of u and v. So if you take the modulus of this means that this is always dominated by, so since Rn is a non-linear space, you can always dominate it by, norm of v, right? So the u dot v, the mod of that is always dominated by norm of u times norm of v. Okay, so this is always true. This is always true. Okay, this is always true. So I hope this is clear. Huh? Okay, that implies this. Okay, so now so this is the first inequality which I need to understand. We need to understand, and the second inequality which we need to do is something called a Gronwall's inequality. Gronwall's inequality. Okay, this inequality, although may seem very out of the place, but this is also a very fundamental inequality which one can actually study in the ODE context. Okay, so what is that? So let's say that let u x px and qx, okay, be non-negative continuous function in the interval x minus x naught less than equal, let's say a, yes, and you also have this relation ux, right, is dominated by px plus integral x naught to x q of t u of t dt. Clear? So you have to have a modulus here for mod x minus x naught less than equal a. So for any x between x naught minus a and x naught plus a, let us assume that ux satisfies this. So ux is always dominated by px plus integral qx ut from x naught to x. Then the following identity holds. Then the following inequality holds. Inequality holds. So what is this inequality? It says that ux is always dominated by px, right, plus mod x naught to x p of t q of t exponential integral t to x q of xi d xi. Okay, and the modulus of that dt. Okay, so basically you see the first relation here, this relation, let's say call it 1, this relation call it 2. See, the first relation is given to u1, 1 is given in terms of u is dominated by a quantity which also depends on u, you see, also depends on u. And the second inequality says that if this sort of inequality holds for the first inequality, then the second will also hold, and the property of second is this: see, u is independent of u on the right hand side. So the left hand side u is there, but in the right hand side there is no u. Okay, so this particular thing holds. Okay, and this is one of the most fundamental results which we have to learn for this course. Okay, so this of course for mod x minus x naught less than equal a. Okay, so this is all hold for all x in between this interval. Okay, so let's look at the proof of this. Okay, so we'll do it. So we do this for this interval. Okay, you can do it for the other one also, exactly the same thing, doesn't really matter. So you can just check the other part also. Okay, doesn't matter. Okay, so we'll do it for x between x naught and x naught plus a, right? So what we do is we define define r of x, new function r of x. How are we defining it? Okay, this is the this is how we write it, define. Okay, we are defining it to be x naught to x q of t u of t dt. Okay, so this particular, you see, q of t u of t dt from x naught to x, this particular quantity we are calling it as r of x. Okay, so if we do that, that will imply r of x naught is of course 0, because integral from x naught to x naught, whatever quantity it is going to be 0, right? And of course we also have that, you see, q and t are continuous functions, right? So fundamental theorem of calculus says that the integral of those, if you define a new function out of it, then it is also going to be differentiable, right? So we can talk about r prime of x, and that will be, by fundamental theorem of calculus, is given by q of x times u of x, u of x times u of x, right? Right, now you see, from 1 what can we say? So from 1 can say that u of x, okay, is less than equals to p of x plus r of x, right? And that we can also write it as this. See, if we multiply it by q of x, then we, and q is you see, q is non-negative function, non-negative function. So all of the functions here are non-negative. Okay, so if you multiply it by q of x, what happens is, this becomes q of x, this becomes q times r, q times u, so which is r, so r prime. So this becomes r prime of x is less than equal p of x u of x plus r of x u of x. I hope this is clear, right? Okay, now you see, this is basically an inequality where it looks like this, no? R prime of x minus qx rx is less than equals to px qx. This is what it means, right? Now you see, this is basically nothing but an ODE, right? And what we can do is, if we multiply, so if we multiply the above with this integral, you see, exponential, so the integrating factor, right? We are just finding out the integrating factor, x naught to x q of xi d xi. Okay, exponential this, we get what do we get? We get that exponential. So basically, let's just call it a phi. Let's just call it phi of x. Okay, this is our integrating factor. That is, okay. We get phi of x times r of x. Okay, did we use phi anywhere? I don't think so. Okay, so we can use it. Okay, so the derivative of that is dominated by p of x q of x and phi of x, right? Okay, so we define phi like to be this function, the integrating factor, right? So once that is there, you see, now if you integrate both sides, okay, what do you get? You get r of x, and this phi of x, 1 by phi of x it will be, right? So this is always dominated by x naught to x p of t q of t, and then this phi of x, I can write it properly, so it becomes exponential of integral t to x q of xi d xi dt. Yeah. So once you have this, you see, so basically this is integrating the above expression. So once you have this, you see the inequality. So you see the difference between this and this is this. You see, this is ux less than equal px times this particular term, right? So, and we also have this particular term. So you see ux is less than equal px plus rx, right? Okay, and rx we already got that is dominated by this. So therefore you have your result. So therefore one has ux is dominated by px plus rx. And what is rx? Rx is again dominated by x naught to x P of t, Q of t, exponential t to x, Q of xi, t xi, dt. Clear? So this is how we are going to get it. Now you see the original expression, this has a modulus sign here. Okay, so that you will get once you do the x naught minus minus a part also. Okay, so once you do it, you put it together, and then we have this Gronwall inequality. Okay, I hope this is clear. Okay, now once that is true, what we can also do is essentially put a little corollary. Okay, corollary here. So you see that if you put in this inequality, if you put p to be 0, okay, so if p of x is identically equals to 0, okay, then what does it mean? It means ux is always less than equal 0 plus x naught to x 0, right? So basically it means that ux is always dominated by 0, but since u is non-negative, you see, u is non-negative, this is what our assumption is, non-negative, okay, that will imply that ux has to be identically equals to 0. Clear? Okay, now another corollary which I am writing without proof. Okay, and what I need you to do is please check this corollary, check this. Okay, you have to do it yourself. So the thing is, let's say the function p of x is non-decreasing, okay, if we consider this p of x is non-decreasing in, let's say, this interval x naught and x naught plus a, okay, and it is non-increasing, increasing in the other part. Okay, what is the other part? X naught minus a to x naught. Okay, then u of x is dominated by p of x times exponential mod integral x naught to x q of xi d xi. Okay, so this holds for all x minus x naught less than equal a. Okay, so I want you guys to check this part. Okay, please do this. This is very easy. You have to just use this Gronwall inequality properly, and you will get the result. Okay, it's not very difficult. Exactly the same sort of thing. Okay, so with this we are going to end this particular lecture.